For about 4 years, starting in 1997, PC computer enthusiasts were subjected to weird CPU packages that looked a bit like overgrown Atari 5200 cartridges. Many people have wondered, why did these things exist? What was the point? And why did they vanish pretty much as abruptly as they arrived?
Tales of weird stuff presents. Processor packages from the fiery pit.
Before I dive into any of the specifics of this topic, I want to take a moment to explain some of the factors that contribute to the performance of digital data transmission systems. I'm going to explain this in pretty much the most generic terms possible because these concepts apply to a lot of things well beyond this fairly narrow topic. Two primary factors affect the measurable performance in a data transfer system: bandwidth and latency. To explain this, I'm going to use a water pipe analogy. So bandwidth is roughly how much water can flow through the pipe in a particular unit of time. Two factors affect this: the cross-sectional area of the pipe and the flow rate through the pipe, which is proportional to the water pressure. If I have a pipe with cross-section area X, and I have another pipe with cross-sectional area 2X, to get the same amount of water out of the pipe, of the first pipe, it has to flow twice as fast as the water coming out of the second pipe. Right? That seems reasonably obvious. Now, in digital data, this is analogous to the bit width and the clock speed. If I transmit data over an 8-bit bus at 10 megahertz and a 16-bit bus at 5 megahertz, it's 10 megabytes per second. Now, there's a few reasons why I might pick one of those over the other. One's more wires. They might be more difficult to route. The other might require more expensive components. There's a bunch of factors. Latency is the time from requesting water come out of the pipe until that first drop appears. Fire hydrant provides a lot of water per minute, but it takes a while from when you decide you need water to it actually coming out. The water faucet in my kitchen doesn't provide that much water per minute, but it comes on pretty much instantly. One is more important for filling a drinking glass, and the other is a lot more important for putting out a house fire. Now, in computer performance measurement analysis circles, we call this workload dependence, and it absolutely applies to all variety of computer performance problems. In this kind of example, sometimes bandwidth is more important and sometimes latency is more important. Right? Streaming video versus online gaming is a really good example. Now, finding the right balance for a variety of workloads at a particular price point can be hard. Really, really hard. All right, now with that out of the way, we get to walk back in time. Back years before the first slot-based CPU was ever even teased at a trade show. We're going all the way back to the early 1990s when the 46 was king of the PC desktop and Pentium was just about to become a household name. For the rest of this video, I'm primarily going to use specific chip or core names rather than the more common names. This is done to minimize potential confusion, yours and mine. There are architectural differences between these specific models that will absolutely matter for this discussion. The original socket 4 Pentium is the P5. The later socket 5 Pentiums are the P54C, and the Pentium MMX is the P55C. Now you can see there a lot happened from socket 4 to socket 5. I will also talk about the Pentium overdrive for 486, which is the P24T. The P5 featured a number of architectural improvements over the 486. Superscalar execution and dramatically improved floating point performance received a lot of the press. Well, okay. FDiv and FOOF got a lot of press too, but that's a different topic altogether. The dramatic increase in computational performance posed a significant problem for the rest of the system. The P5 was operating on the same memory and main memory and cache memory technology as the 486. Now, numerous videos on this channel and on lots of other channels have demonstrated what people already knew in 1992. Size and speed of L2 cache matters, right? Adjusting that from 2 ticks of latency to 1 tick of latency, that absolutely matters. You can measure that. Super fast SRAM necessary to make a huge L2 cache was still really expensive. So just, slapping a megabyte of the fastest possible SRAM chips on a motherboard destined for a desktop PC was not going to happen. Creating that cache with existing SRAM technology also wouldn't fully solve the problem. To account for this, the P5 includes a number of important features. One, the on-chip L1 cache is much larger. The 486 had a unified 8K L1 cache that is shared by instructions and data. The P54C had a separate 8K L1 instruction cache and 8K L1 data cache. The P55C would double this to 16K and 16K, and this dramatically decreased the dependency on main memory and on the L2 cache. Number 2, the width of the bus was doubled from 32 bits to 64 bits. This doubles the potential memory and L2 cache bandwidth, but it does nothing for latency. And finally, the bus speed was basically doubled to either 60 or 66 megahertz. This increases the potential bandwidth and decreases the potential latency. I think the initial P5 systems, the 60 and 66 megahertz Pentium, added an extra wait state, so the bandwidth was increased, but it wasn't quite doubled. I'm not 100% sure about that. Now, since the CPU is able to communicate with the L2 cache controller, the chipset, twice as fast, the latency is definitely decreased. Now, there are a few other enhancements to the Pentium L2 cache protocol, but those mostly affect multiprocessor systems and interactions with DMA devices and bus master devices. So discussions about the MESI protocol are quite a bit outside the scope of this video. We could directly measure the effects of bus width and bus speed by comparing the performance of a 66 megahertz P5 and a 63 megahertz P24T. They're not exactly the same core, but they are very close. Now, doing that full round of benchmarking is also way beyond the scope of this video. I'm pretty sure that this is going to be a pretty long video without a huge pile of benchmarks, but doing that benchmarking is definitely on my to-do list. I'm very curious to see what sort of results will come out of doing as apples to apples as possible comparisons. Basically isolating for as few differences between the configurations as possible. If you are interested in seeing a video like that, I highly recommend you subscribe to the channel. Anecdotal evidence around the internet suggests that the faster 83 megahertz P24T performs about like a 66 megahertz P5. So this would probably slightly outperform this 60 megahertz example, with everyone running at their standard clock speeds. A very reasonable hypothesis is that the majority of this speed difference is the the width and clock speed of the memory interface. Like early pre-DX2 46 CPUs, the P5 ran the CPU core at the bus speed. In other words, they all had a 1x multiplier. They both had a 1x multiplier. And even the enhanced P54C maxed out at a 3x multiplier for 200 megahertz. So the resulting core speed is pretty close to the system bus speed. Looking at data across CPUs of this family, we can see a startling trend. Now, I pulled whetstone data from CPUworld.com across all of the P54C processors, and I've charted this data as whetstones per clock versus clock multiplier. And this chart shows pretty clearly that as clock speed increases, the performance per clock decreases. The faster CPUs are faster. It's not directly proportional to the clock speed increase. This effectively sets an upper bound on the useful clock speed for a particular system architecture. Sure, it might have been possible for Intel to create a P54C with a 4.5x multiplier to run at 300 megahertz. But at a 66 megahertz bus with the existing memory technology, the speed increase over the 200 megahertz CPU would not have been significant enough. Now, I'm sure that someone out there has overclocked a P54C to 300 megahertz, and this surely required using very hand-picked RAM, probably using a system that could use SD-RAM, and massively overclocking the bus. And even at that, I am sure that in benchmark results, the speed up is nowhere near the 50% that the clock speed increase is versus the 200 megahertz P54C. If the P55C, the Pentium MMX, is added to the mix, a couple of things are noteworthy. First, whetstones per clock is higher at each matching clock speed. The P55C doubles the amount of L1 cache and adds some other architectural improvements. Second, the whetstones per clock still decreases as clock speed increases, but it decreases at a much lower rate. While this is significant, it kind of just reinforces what we already believe to be true, and that's increased L1 cache size decreases the dependence on the rest of the memory hierarchy. So if we want to improve processor performance, really system performance, where does that leave us? What are our options? Well, we could make main memory faster. And I think everyone watching this video knows that has been happening. And it's just not enough. There's a lovely graph in the first chapter of Hennessy and Patterson, the classic computer architecture textbook, that plots the increase in processor performance and the increase in memory performance through time. Spoiler alert, since 1980 there has been a gap, and that gap has gotten bigger every year. If you're interested in learning a lot more about this topic and about computer architecture, I've put an Amazon affiliate link in the description so you can get your own copy of Hennessy and Patterson. It's a classic for a reason. What else can we do? Well, we could make main memory wider. Well, that's also happened, but it too has limits. Limits both in terms of what is possible and in terms of how much it can help, right? Assume we could make memory infinitely wide. Well, that would give infinite bandwidth, but it would do nothing for latency. Now, the DEC 3000 Model 500 that I have, did a video about this last year. It came out in 1992, a year before the first Pentium, it has a 256-bit wide memory bus. That's 4 times as wide as the measly 64-bit memory bus in the Pentium. Now, the Alpha CPU itself only... I could not even pretend to say that with a straight face. It only has a 128-bit wide bus. So based on what I have read about the architecture of this particular system, it works in a way a little bit similar to the way that a modern DDR system would work, in that all of the memory gets sent the same address at once, and it all comes back into the chipset at once, 256 bits wide, and then the chipset feeds on one clock cycle, feeds 128 bits of the data into the CPU, and then on the next clock cycle feeds the next 128 bits. It's a little bit different than DDR. DDR operates on different edges of the same clock, but it's the principle is close enough that I think the analogy works. Now again, in this alpha architecture, it has massive amount of bandwidth, but the latency is still limited by what that existing DRAM technology can provide. In addition, somebody has to figure out how to route all those wires. And when I was looking around inside that machine, it was a beast. Like, that must have been a nightmare to route all the traces on that motherboard. And so you've got a hard physical limit. The wires have to be somewhere. So, I mean, maybe you could make a 512-bit or a 1024-bit wide memory bus, but on the technology of the early 90s, I mean, forget it. Right? Because not only do you have to figure out where to put all those wires, you have to manufacture it. In the money is no object arena of super high performance computing, that's not as much of a problem, right? You're not going to make that many of them. Digital did not ship as many alpha systems as a single PC manufacturer did in the 90s. Like, a single PC manufacturer, right? So the volume equation is completely different. And so that means you don't have to worry quite as much about yields, and you can put more money into the manufacturing, right? You don't have to be cheap on each one. And also, let's not forget, you're going to charge a small fortune for each one of these computers. Right? People are willing to pay a premium for performance that's not possible through any other means. I mean, how much of a fortune did we spend on a massive rocket to go to the moon? Because there was no other option to get there. Okay, so what else can we do? Well, I mean, we could add more L1 cache, right? We've already seen that increasing L1 cache from the P54C to the P55C made a pretty dramatic improvement in performance. And this does happen too, but it also hits on some hard limits. L1 cache needs to be very low latency, and one of the things that determines the latency of any cache, L1, L2, L47, is the amount of time that it takes to determine whether or not a particular memory address is stored in the cache. And there's a number of strategies for this. The 46 and other similar CPUs of the era, like the Motorola 68040 and a handful of other similar CPUs of that era, used a technique called direct mapped cache. So in this kind of architecture, if the cache has, say, 128 locations where it can store data, so that 8K cache isn't storing data a byte at a time. They're broken up into chunks, so there's fewer than 8K locations. It's 8 kilobytes divided by how big of a chunk gets stored in each location. So we'll say, just to make the example easier, we'll say our cache has 128 locations. So some memory location X will be stored at maybe cache location X mod 128. Now, main memory location X plus 128, so 128 cache lines later in main memory, will also get stored at that same location, and X plus 256, and etc. So if X is stored in the cache when X plus 128 is accessed in the direct map cache, X gets kicked out, X plus 128 goes in that location. Now, some extra data is stored by the cache controller so that it knows what data is in each cache location. On 486 motherboards, this is the tag RAM that you would see. The data that gets stored there is usually the main memory address divided by the number of cache locations. So if you're at cache location, X mod 128, the data that gets stored in the tag is X divided by 128. Now, some architectures not only, so that effectively chops off the bottom bits that aren't necessary, and some would also chop off the top bits. And that's why some early Pentium boards had a limit on how much RAM could be cached, because they didn't want to store the whole address. They just stored a chunk of it and chopped off the rest. So if your memory address was past, I think those motherboards topped out at 64 megs. So if you had more than 64 megs, everything past that point was like, nope, that is not going to go in the L2 cache because we can't tell the difference between address 64 megabytes plus 1 and address 1. So that's a bummer. Now, as you might already be able to imagine, there are certain kinds of memory access patterns that are actually very common for data, not so much for instruction cache, that can cause a direct map cache to perform very, very poorly. So if a program repeatedly just kind of walks through memory and accesses X plus 128, X plus 256, etc., each access, the cache will have to read that new memory location, kick the old thing out of the cache, read the new memory location, kick the old thing out of the cache, and sort of continuously do this bookkeeping, which takes time, but not get any benefit. So the cache can actually slow you down. It's also possible to have memory access patterns that don't fully utilize the cache. I mean, if you never accessed some memory address that is, in this cache example, that is X mod 128 equals 127, right, to hit that 127 slot in the cache, nothing's ever going to get stored there. So your 8K cache isn't fully being utilized. Some of that expensive SRAM in your processor is being wasted. Now, the strategy for mapping an address to a cache location, there are a bunch of complex strategies for doing this. People have gotten PhDs for researching, hey, we found a way that's, 1% better. And so a lot of these strategies try to optimize either cache utilization or, kind of this memory aliasing problem that leads to the spurious evictions. This has a lot of similarity with hash strategies for hash tables in software. There's a lot of differences, but the 10,000 foot view is they're pretty similar. The P5 and the P54C use a two-way set associative L1 cache. In set associative cache architectures, each cache location has some number of slots where multiple memory addresses can be roommates, I guess. So in a two-way set associative cache, instead of having, so in a direct map cache, if you had 128 locations, in a two-way set associative cache, you might have 64 locations, but each one of those locations can have two different memory addresses there. So now, when a memory request comes in, it hashes to a certain cache location, and instead of checking, are you the thing, it has to check two. Are you the thing? Are you the thing? In a four-way set, it would have to check four, etc., etc. Now, because there are more entries, the cache controller is doing more work to determine whether the requested address is in the cache. When an entry not in the cache is requested, it will replace one of the existing entries at that location. And the most common strategy is to pick the one of the two in the two-way set, to pick the one that was least recently used. They call this LRU, least recently used. Now, increasing the set associativity improves the probability that all the cache will be full of useful data, because there's fewer slots to map addresses to. And it also reduces the rate at which data that might be needed later will be evicted, because you now get to pick. Instead of just saying, you're the one here, you're out, there's several there, and you get to pick one, and you get to try to pick the one that's, least recently used, so probably it won't be used again soon. And all of this reduces the dependence on the rest of the memory architecture, on the rest of the memory hierarchy at a cost. And that cost is either a linear increase in cache latency, because are you the one? Are you the one? Or an exponential increase in the amount of hardware to do all those comparisons at once. So at some point, I may do an even more in-depth video about various cache architectures. If you're interested in seeing that kind of video, leave a note for me in the comments below. L1 caches on modern processors haven't grown that much. The L1 cache on an Intel Raptor Cove core from 2022 has only 32K for instructions and 48K for data. So in the 25 years, the 25 years since the P55C, the L1 cache size hasn't even tripled. Now, in that same time, the cache architecture has migrated from a 4-way set associative cache in the P55C to a 12-way set associative cache in the Raptor Cove. So it is a direct linear increase there. That exponential increase in transistors is a bit of a deal breaker. In that same time period, the total number of transistors in a processor, so going from that P55C Pentium MMX to a modern Core i7, we've gone from about 4.5 million transistors to something on the order of 12 billion. So we got a 3x increase in cache size for a 2,600x increase in total transistors. Okay, so we're starting to exhaust all of the options. We're forced to look at the L2 cache. It needs to get bigger. It needs to get faster. Or actually, it needs to get both. Right? Now, bigger L2 cache likely means a linear increase in cost and board space. Chip density on cache has increased or was increasing, but they're still big chips. They still have got to take up a bunch of space. And bigger L2 cache at existing speeds doesn't increase the performance per clock cycle decrease as clock speed increases. That L2 cache has to get faster. So in this context, faster means both. Right? It has to both get more bandwidth and less latency. So if CPU clock speed is going to increase, latency has to decrease with it, right? The wall clock time that it takes to get data from the cache has to decrease in order to have the same number of the same amount of clock cycle latency. And ideally, you want the clock cycle latency to get better. Now, this boils down to getting 2 or more chips to talk to each other faster. And that's a fundamentally hard problem. The time that it takes electrons to get from point A to point B, noise in circuits, power usage, and a whole heap of other factors put a limit on how fast things can go. Now, propagation delay and noise are probably the 2 biggest issues. And one thing that helps mitigate both of those issues is decreasing the distance between the chips, right? If it takes a certain amount of time to get from point A to point B, like put point A and point B closer to each other, right? So this is also an ongoing trend. Early processors were made of a bunch of individual transistors or vacuum tubes or something. We're going to skip. Early processors were made of a bunch of individual chips spread over a handful of circuit boards. The CPUs in the Centurion mainframes over on Usagi Electric, they're made of a handful of bit slice chips that implement part of the processor, and then they're kind of cobbled together with a bunch of additional logic to make a whole CPU. Now, having that whole thing spread out across an entire board limits how fast the clock can go, and putting everything on a single piece of silicon dramatically increases the clock speed potential. Okay, so the first obvious idea is to put the L2 cache on the same piece of silicon as the CPU. I mean, you can't get any closer than that. Well, the modern CPU designers work to figure out the routing so that even on the die, they can get the L2 cache optimally placed relative to the CPU. That's jump right. Moore's law would eventually get us there, but that's jumping way far ahead in the story. And we obviously do get there, and a substantial portion of those 12 billion transistors in that modern processor is the 24 megabytes of L2 cache. But in the mid-90s, like, the manufacturing technology wasn't even close. Let's pause this part of the story for a moment, and let's take a look at what was happening elsewhere in the industry. Well, quite a few high-end workstation and server CPU vendors had already picked up on the idea that putting the L2 cache physically close to the CPU made higher clock speeds possible. Now, again, these systems were manufactured at lower volumes with cost is no object. I mean, that's an exaggeration, but these systems came at a substantial price premium for the performance that you were getting. And in general, a lot of those systems came of the form, it comes in this model and you get what you get and you don't throw a fit, right? That DEC 3000, there were a couple of models, and once you bought one, like, that was what you had. There was no, we want to upgrade the CPU, or we want to add a CPU. There was none of that. Now, a few vendors like Sun and SGI made systems that could have various CPU configurations that were maybe user upgradable, or maybe a service tech could upgrade their system, that had tightly coupled CPU and L2 cache. And these systems featured the CPU and the L2 cache on a small circuit board that connected to the motherboard. So here's an M-Bus CPU board for a SparkStation 10 from 1992. Here's where it connects to the motherboard. And then this is the motherboard and the CPU board for an SGI Indigo in 1993. The CPU is hiding under this heatsink, and you can see the cache chips hanging out over here. And in effect, Apple was doing something fairly similar too, with PDS, the processor direct slot. High-end Apple, Macintosh accelerators that used PDS, it was a small board that had the processor and had some tightly coupled cache on the same board that you plugged into the motherboard. That's not quite exactly the same, but it's somewhere on that arc. And certainly what Apple was doing in the days of like the G4 Power Macs was right in line with this, where the CPU and the cache and all of that was on a small board that plugged into the motherboard. Now, Intel, they decided to do something different. Now, in most of these architectures, the CPU and the L2 cache communicate very quickly, but still much slower than the CPU core clock speed. And when Intel decided to make a first real go at the high-end workstation and server market, they swung for the fence. Full speed L2 cache or bust. So if you don't have the manufacturing to put the CPU and the L2 cache on the same die, and putting the CPU and the L2 cache close to each other isn't fast enough, put the two chips in the same package. And thus the Pentium Pro was born. Back in the day, I upgraded from a dual Pentium 133 megahertz system to a single processor Pentium Pro 166. My chip was actually an overclocked 150 megahertz processor, very similar to this one. Now, when I made that upgrade from the dual Pentium system to the single Pentium Pro system, I don't remember multi-threaded things being faster. I compiled a lot of C programs, and so that is an embarrassingly parallel problem. You can spread that out across a bunch of processors at once and get nearly linear speed up. I don't remember that kind of thing being very much faster, but boy howdy, anything that was single-threaded, it is one of the few times that I have made an upgrade from one reasonably modern CPU to another modern CPU and just been blown away by the performance increase. I couldn't believe it. I could not believe how much faster it was. I want to say I probably bought that in 1997, maybe early 1998, but I'm pretty sure it was 1997 based on where I think I was living at the time when I bought it, and what games I was playing. I got it used, I got a very good price on it. But when that CPU, just that CPU, was released in 1995, it would have cost almost $1,000, and that's $2,000 in today's money. These CPUs were expensive for a few reasons. First of all, there's two big chips on it that cost a lot to develop and a lot to manufacture just those chips, right? They're very big, so you don't get a lot of them off of a single wafer, so they're expensive each. And secondly, and this is the real killer, the way that those chips were designed, when they came out of manufacturing, you couldn't test either one until they were connected to each other. You couldn't test the memory without the CPU, and you couldn't test the CPU without the memory. And the only way to connect them to each other was to put them in that piece of ceramic. And by the time they're in the piece of ceramic together, you've reached the point of no return. If either chip is bad, you have to toss the whole thing. And so, especially early on, yields were bad. They were bad. And so they had to charge a huge pile of money for each one that actually did survive testing. Now, I don't know if the Pentium Pro L2 cache was doing the trick that a lot of other CPUs have done since then, where if there was a small bit of defect, they could just disable half the cache, and so they would bin things. I have no idea about that. If you have any firsthand information about that, I would love to hear about it in the comments. Because that might suggest that some CPUs, some 256K CPUs could get upgraded into 512K CPUs. Now, the 1 megabyte CPU that would come out a bit later used 2 512K cache chips, and that just exacerbated the problems. Now, if any one of 3 chips was bad, the whole thing was trash. There is a reason that those CPUs cost $2,700 when released in 1997. Now, I suspect that yields of the individual chips were quite a bit better by then, that things had improved in the intervening 2 years, so it might not have been quite so bad, but I mean, still. Now, that 1 megabyte CPU, and the 1 megabyte cache CPU, is kind of interesting. There was a lot of industry speculation that by 1997, the Pentium Pro would hit 250 megahertz. That CPU never materialized. Instead, we got a 200 megahertz CPU with 1 megabyte of cache. So I wonder what were the problems that led to that course change. Could one or both of the chips just not reliably run at 250 megahertz? Was the performance increase of jumping up to 250 megahertz not worth it? Now, I have a pair in another system around here. I have a pair of 180 megahertz CPUs that are rock solid overclocked to 210 megahertz. So 250 megahertz doesn't feel like that much of a stretch. Now, the 180s and the 150s both are only come as 256K cache, and the 166s, I believe, only come as 512, and the 200s come in all 3 possible configurations of cache. Now, by the time those CPUs came out in 1997, I was working at Sequent Computer Systems, where I had access to a machine that I am pretty sure had 64. It might have only been 32, but I'm pretty sure it was 64 200 megahertz 512K Pentium Pro CPUs. Now, I never thought about it at the time, but that's $127,000 of just processors. Money is no object, am I right? Now, that wasn't going to fly in the desktop market either. Like, a single high-end 200 megahertz Pentium Pro CPU cost as much as an entire 200 megahertz Pentium system. Like, that was not just no. So, well, maybe Sun and SGI and literally everyone else in the industry had the right idea after all. Like, put the CPU and the cache on a small circuit board that would connect to the motherboard. They get manufactured and packaged together. You can test the chips independently, right? You know that they're properly matched, that they're the right speeds for each other. Users won't have to worry about if the cache on the motherboard is fast enough to work properly with the CPU, right? That was an issue with 46s. Like, you got a fast 46 that maybe had a 40 megahertz bus, and your cache is too slow, so it doesn't work now. Or you have to add a bunch of wait states, or some kind of problem. It was a very neat and tidy solution. There's just 2 problems. Just 2. First, it's still too hard to get the cache to run at the full processor core speed without going to heroic efforts. And by heroic, I mean expensive. As a result, all of these slot CPUs, both from Intel and from AMD, The off-die L2 cache runs at half the CPU speed. This is still far greater than the bus speed, but it can't match the power and performance of running at the full core speed. Second, how do you want to package it? And that has a big impact on OEMs that are making systems and that are manufacturing motherboards. I honestly don't know why Intel did this instead of this. To the best of my knowledge, only 3 companies have ever done this: Intel, AMD, and Digital. There were some alpha processors released in a package similar to this, and I hope to do a video about those CPUs someday. They're very rare and hard to come by. My only hypothesis is that the vertical arrangement makes it much easier for multiprocessor configurations. When Apple or SGI manufactured multiprocessor boards, both processors were on the same board. Now, there are advantages to this because then you can definitely get the CPUs closer together and the CPUs can communicate faster, but it makes it a lot more expensive to upgrade a single CPU configuration to a dual CPU configuration. And it makes it more expensive to replace a single faulty CPU in a dual CPU configuration. Sun and Bus can have 2 CPUs on a single board, like this one. And there can be 2 boards per system. The boards end up being kind of stacked over top of each other. And that does pose some airflow and heat problems. The SPARCstation 10 is especially notorious for this with faster CPUs. It wouldn't be a problem with these particular CPUs, but some of the later higher clock speed CPUs, it was a huge problem. Now, remember when I mentioned heroic efforts before? Well, there are Pentium II and Pentium III slot CPUs that have cache that runs at the full core speed. These are the Pentium II and Pentium III Xeon processors. Like the Pentium Pro before them, these were expensive. This particular one is a Pentium III Xeon, 550 megahertz, 100 megahertz bus, 1 megabyte L2 cache. The 400 megahertz slot 2 Pentium 2 with 512K cache, the same amount of L2 cache as its slot 1 counterpart, was over $1,100 at release in June 1998. Xeons were available with 512, 1 megabyte like this one, and 2 megabytes of L2 cache. That L2 cache was a special, very specifically manufactured chip that pairs with those Xeon processors. It is a special thing manufactured on, as far as I'm aware, on the same manufacturing technology as the CPU core. And usually the top end manufacturing, like the only thing that gets made on that, at least back on the day, was the CPUs. And then, last year's technology is what you used to make your SRAM, and the year before that is what you used to make your DRAM, and so on. Now, I have a few Xeons, maybe 5 or 6 total, and I'm working on rounding out the collection so that I can do a massive cross-comparison between the various Pentium 2 and Pentium 3 Xeons and the slot 1 Pentium 2 and Pentium 3 processors. Now, I teased that a little over a year ago. I am still working on it. It is a very long-term project, but it's gradually getting there. Let's be honest. AMD did copy Intel, but I don't think it was so that they could seem cool like Intel. I think it was quite a bit more pragmatic than that. The physical package and the connector is the same, but the connector is actually reversed. They're not pin compatible, but the physical connector is is reversed. So it's not physically possible to put an AMD CPU in an Intel slot or vice versa without, if it won't fit, force it. If it breaks, it needed replacing anyway. I believe they did this purely for economy of scale kind of purposes. The connectors and the brackets and all of the physical stuff is weird. And they're not used for anything else. So knowing that realistically they were going to sell fewer units than Intel, using the same package and the same kinds of components allowed motherboard manufacturers to save a little bit on each board, because they could just order the same parts for the AMD boards and the Intel boards, order them in bulk, and get a better price on it. And so I think my guess is AMD knew that, and they knew that making it a little bit cheaper to manufacture boards for their processors would encourage motherboard makers to do that. Now, I also suspect that these kinds of packages were always viewed as a stopgap. I can't believe that any engineers or even any marketing people at AMD or Intel wanted this kind of packaging, right? What they wanted was something like the Pentium Pro, but they wanted the L2 and the CPU on the same physical die, right? That had all of the advantages, right? It was going to be faster. It was going to be cheaper to manufacture. It was going to be more scalable. Like it had all of the advantages. They just couldn't do it yet. But it turns out, I think that future, that power of yet, was a little bit closer than they had initially anticipated. The first slot 1 Pentium II CPU was released in May 1997. It had 512K of half-speed L2 cache, and it cost $636. Expensive as that was less than 1/4 the price of that 1 megabyte 200 megahertz Pentium Pro CPU. Now, in August 1998, like just 15 months later, like not even a year and a half later, the Mendocino Celeron was released, and it had 128K of full speed on-die L2 cache. And people figured out pretty quickly that you could overclock that 300 megahertz CPU to 450 megahertz 100% of the time with basically zero effort, and the performance was outstanding. It was, on the majority of workloads, it was faster than, my recollection is, it was faster than a 450 megahertz at the same clock speed Pentium II with 4 times as much half-speed cache. So that extra speed made a huge, on a lot of workloads, not on every workload, but on a lot of workloads, it was faster. that cannot have made Intel happy. So that was the first sounding of the death bell for those slot-based CPUs. Because if you can put it all on a chip, like, it's not that long until we're back to CPU sockets on the motherboard, and those extra daughter boards are out. Now, a year later, the Pentium II Overdrive was released. Now, this put a 333 megahertz Pentium II in a Pentium Pro socket. Now, this CPU is special because it has 512K of full speed off-die L2 cache. It's essentially a Pentium II Xeon in a much smaller package, right? It's a Pentium II Xeon in that socket 8 package instead of in the giant slot 2 package. I'm a little bit surprised that there was never a slot 1 version of this CPU. Now, there were some very, very rare, and I would love to get my hands on two, Slocket adapters that could have allowed the use of that CPU in some slot 1 motherboards. And I feel like that CPU in, either in a socket adapter or just manufactured for slot 1, would have been a good upgrade path for early adopters of the slot 1 platform. People that were on either really old 440FX or 440LX motherboards that were limited to 66 megahertz frontside bus. I mean, Socket 5 got all kinds of cool Pentium MMX upgrade, overdrive CPUs. Why not the 66 megahertz slot 1? 1999 rang the death bell for slot CPUs 2 more times. In February, AMD released the K6-3 processor. This was an evolution of the K6-2 processor, and it featured 256K of full-speed, on-die L2 cache. And I've always thought it was interesting that AMD's first CPU with on-die L2 cache was released 4 months before its first slot-based CPU. I'm just curious about what happened that in the parallel development. I mean, those processors were developed by different teams. I'm just curious, like how they ended up at that, because it seems a very non-ideal position to be in. Now, in October, Intel released the Coppermine Pentium III. These processors also featured 256K of on-die L2 cache, and they would be released for both slot 1, they'd be released for slot 1, slot 2, and eventually socket 370, but that's a different video. The 900 megahertz Pentium III Xeon non-Coppermine with 2 megabytes of L2 cache was released much after this, in March of 2001. It was the last Intel CPU released in a slot form factor with off-die L2 cache. And I hope you're sitting down for this, but that thing cost $3,700. And they are very collectible, and they are not cheap today, but they do not cost no $3,000. And the rest, as they say, is history. We've completely abandoned slots or processors on tiny little boards or any of that, and it's sockets. But now, instead of putting the L2 cache as close as possible to the CPU, memory is put as close as possible to the CPU, and the memory controller is on the CPU. So this progression continues. Everything that's old is new again. Now, if you enjoyed this video, please slap that like button. And if you had any feelings about this different sort of educational lecture conference, I don't know what to call this format, but if you have thoughts about this, go ahead and share them with me in the comments below. My next video, I'm going to get back to my usual shtick. I've got a bunch of other computers that need fixing and some weird, goofy, offbeat parts to look at and a whole bunch of stuff to do. That's all coming back. But until then, try to remember the good stuff. Water come out of the pipe until you get the first stripe. It's almost funny now.